All right. Oh, there we go. Hello and welcome to United Astronomy Clubs of New Jersey. Uh, while I see a couple people I think are down there coming in, I just want to go over a couple things for our online audience or for those of you who are here. You can always check us out on our website, uacnj.org. That's where you'll find a whole list of our upcoming talks we've done in the past, information on any scopes and equipment we have on site, as well as a list of all our member clubs and out various chances to get in contact with us and outreach opportunities. You can also check us out on our social media pages: Facebook, Instagram, Twitter, Discord. Uh, and as always, we are a nonprofit, so everything you guys have done to support us, whether by just tossing a like down there in the YouTubes, like, subscribe to our channel, or just commenting and being here with us, we greatly appreciate it. All right, so since it looks like we have most of our live audience here settled down, a couple of safety tips. If you need to use the bathroom, we have the porta potty to my right, your left. It is lit up nice and red. We also have a little gift shop and museum area over to my left, your right. And after stream, I'll be over there for a bit where you can check out things. And like I said, any proceeds from that does go to keeping our lights on and allows us to keep offering free public programs. When we do go to leave, please use your headlights. We like not getting run over, and I'm certain you also would prefer not getting run over. That being said, if you do have a flashlight, try and keep the light pointed towards the ground. We don't need to unnecessarily blind people. Night vision is something that takes a while to adjust, so as much as we enjoy headlights so we don't run people over, we don't need to add to the light pollution. That being said, we do have volunteers with scopes open tonight. Do listen to them. Do ask questions. They love questions, and they love making up answers. I personally use my magical electronic handheld box. But that's besides the point. Tonight's presentation is about the James Webb telescope with Walt Windish here. And now that I can actually see it, Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1985, just in time to see Halley's Comet. Walt's a member of the North Jersey Astronomical Group and the Rockland Astronomy Club, and has been coming up to Jenny Jump for over 20 years, and he's going to tell us all about what the James Webb has been up to.
Well, thank you, and good evening. I believe I'm on, right? All right, there we go. Okay. Good evening, and thanks for coming. How many of you are camping tonight? Anyone? All right, excellent. Boy, you picked a great weekend for camping. Wow, nice. Well, what I'd like to do today is talk about the James Webb Space Telescope. It's been up there a couple months, and NASA has changed its tactics. Instead of reviewing a lot of the pictures before it sends them out, they've been just sending a lot of images out. And so I've taken a few of them that I think match the main mission. So we can talk about the mission, we can talk about the telescope compared to Hubble, and maybe even talk about a little bit of the science behind it, so you could better understand what you hear when you have a news story going on. So the telescope's mission duration is about 5 to 10 years. But if they've built it as well as they have the other telescopes and other stuff out there, we can expect a much longer lifetime than that. The Webb's primary mirror aperture is about 25 square meters, broken into 18 segments, giving us about an aperture 3 times the size of Hubble. Focal length, for those who are interested, is 131 meters, and the mirror is made of beryllium plated with gold. And as big as that mirror is, the gold weighs only 48 grams, which is less than 2 ounces. So that's a really thin layer of gold on that mirror. So let's just take a look at a little bit of science so we can understand exactly what we're looking at. The electromagnetic spectrum goes all the way from gamma rays all the way up to AM radio and beyond. And our eyes can only see a little piece of that called the visible light. That's this little tiny piece here. So in longer wavelengths, you get up to microwave, aircraft, AM radio, infrared. On the shorter wavelengths, we go from UV light all the way up to gamma rays. So although we can't see anything but visible light, and we really can't even see that very well because our eyes act like a camera at 1/30th shutter speed. So when you look at a telescope at a lot of objects, you won't be able to see the color. You'll see stuff that looks like milky white and white cloudy kind of stuff. But a camera on a telescope can stay open for hours and collect enough light so you can really see that spectacular color that you're used to seeing. And we can also put instruments on the telescope that record other wavelengths, ultraviolet, infrared, and that makes all the difference in the world in looking at objects out there. It gives us a lot more information than just our eyes can see. I'll give you an example, and these are some Hubble images, but I like to use these to show you the different wavelengths. That's visible light. That's the Eagle Nebula in the constellation Serpens. It's taken in visible light by Hubble. It's about 6,500 light years away. Now Hubble also had a near infrared sensor on it. And take a look at the exact same frame, but in near infrared. Quite a difference. I mean, here, the Eagle Nebula is a star factory. The dust that we see compresses. It finally starts compressing on its own gravity, and when it gets tight enough, big enough, it ignites into nuclear fusion, and we see stars popping into existence. So we can start to see a lot more stars, not only in the background, but also the new stars that have been born in this cloud. So here's a side-by-side comparison. Visible light on the left, near infrared on the right. Both give us important information for studying this object, but if we only had one instrument, we'd be missing a whole lot of the picture, wouldn't we? So here's one more comparison. Visible light on the left, infrared on the right. It's the Carina Nebula, and again, both images were taken by Hubble, but you can see the infrared, which is heat sensitive, really slices through that dust and gets us behind the dust that's obscured in the visible light range. Now this image of the Tarantula Nebula was, it's so called because of the bright filament supposedly looking like a tarantula. Understand a lot of these objects were named before we had the Hubble up there, and in a telescope sometimes they look more like the objects they're named after than when you see so much detail. It really it gets a little confusing. But this is another birthplace of stars. This is another star factory. A lot of young bright stars in the field of view. It's located in the Large Magellanic Cloud, which is a small companion galaxy to the Milky Way. So it's pretty close. It's close enough to Earth that individual stars can be resolved with the telescope, which means that we really can start to study the life cycle of stars and get some great resolution here. This Hubble image was taken in 2017, and again, it reveals many young stars that scientists have used to study stellar evolution. So they took the James Webb and they pointed it in this area. Especially this cluster is very interesting to scientists. So they pointed it right there, and they came up with this image. And you can see, and if you have a computer, you can see even more how much resolution. But you can see all of these young stars in there that just give a lot of information. This picture is about 340 light years across. So that means it takes light 340 years to go from one end of this picture to the other end of the picture. That's a pretty big jump. A light year is about 6 trillion miles. So big distance. Um, tons and tons of never before seen young stars that were previously shrouded in the dust, because the James Webb telescope is focusing on the infrared, not only the near infrared but mid infrared. So this was built really to start cutting through a lot of the dust and not concentrate as much on the visible light, because the Hubble's been looking at that for 37 years. And even though it's not as big a light bucket, we've gotten a lot of great images out of Hubble, in especially in the visible. So here's the spectrum that I showed you before with a couple of the telescopes. We have it covered pretty well. We've got, in the largest wavelengths, we've got the very large array, which are radio telescopes. There's 27 of them hooked up, giving us a huge aperture of miles the way they're hooked up. We've got microwave here. We've got the Swift on gamma rays, the RXTE on X-rays. Here's the Hubble planted right in the visible, a little bit of ultraviolet, a little bit of infrared, and then we've got the James Webb, which is really solidly in the infrared. We've got the near infrared, called near infrared because it's near the visible spectrum, and then there's the mid infrared. That's the main areas, and it also has a spectrograph, as I'll mention later on. So NASA doesn't consider the James Webb scope just a replacement for the Hubble as much as a successor to the Hubble. The Hubble made important scientific breakthroughs and had more than its share of scientific surprises. And we have every reason to believe that the Webb telescope is going to be full of surprises that we had no idea were out there. The Webb primarily looks at the infrared, as I said, which extends further out than Hubble was taking a look at. And the discoveries from the Hubble wanted us to explore longer wavelengths. We wanted to look further into the infrared because of what we saw with the Webb scope, because it not only cuts through dust, but it lets us take a look at objects that have greater and greater redshifts. So what's a redshift? I'm glad you asked. So a redshift is part of the Doppler effect. Sometimes it's called a Doppler shift. If you're standing near a car and a race car is coming near you, as it comes near you, you hear it increase in pitch. And then as it passes, you hear the pitch go lower. Right? So what's happening is, as the race car is coming towards me, those sound waves are being compressed, as we can see this foolish young guy standing in front of a police car. We can see the sound waves are compressed, which means they go up higher in pitch. So even though stationary police car would make the same noise, as it's moving, we either hear the pitch go up, or as this person, wiser person behind the police car, as it moves away, these waves get stretched out, and so we hear it lower and lower in pitch. That's called the Doppler effect. Well, light acts in the same way. So when we're standing on Earth, if there's an object that's coming towards us, the light that it's giving off is shifted towards the blue. And if it's moving away from us, it's shifted away towards the red. And just about everything is shifted away from us. The universe is expanding like a balloon that's being blown up. So everything's moving away from everything else. And so just about everything has a redshift. And the higher the redshift, the further away it is and the faster it's moving away from us. And those are equal. If something's farther away, it's moving away faster. Now, locally, there are some things that exhibit blue shift because they're moving towards us. There's some stars in our galaxy that are moving towards us, and then there's also the Andromeda galaxy, which is our closest galaxy, which is moving towards us at a speed of about 402,000 kilometers per hour. So in about 4 billion years, it will collide with the Milky Way, and scientists call that what was it? The Milkomeda. galaxy. But don't worry about it. By the time the Andromeda galaxy gets that close to us, the sun will have gotten hot enough to pretty much boil everything off the surface, and maybe just the cockroaches will be able to see that spectacle. But how do we turn this redshift into something that we can measure? You know, how do we know what the original frequency of that light is, that to know that it's been shifted one way or the other? Well, what we do is if we discharge an electric current and then run it through a slit, a narrow slit, and thank you. I got the clips. And if we run it through a narrow slit and then through a prism, it gives a very distinct bars of color, which is called the spectrum. And each element gives a different spectrum out. And so here we see this is what hydrogen looks like. So the universe is 75% hydrogen out there, 24% helium. That's 99% of the elements. And so this is what hydrogen looks like. And there are very distinct frequencies that are being emitted when it's excited like that. And of course, stars are plenty of excitement, so the hydrogen in the stars give off the same spectrum. And so the spacing between the hydrogen lines doesn't move. But as the redshift increases, as the star's moving faster away from us, the entire spectrum shifts. You see that? So the spaces are the same, so we know, okay, that's the hydrogen signature. Even if the frequencies of these lines are different, something moving quickly and farther away, they're really shifted towards the red. Because of the spacing, we know that that's a hydrogen spectrum. And so then we can measure what the redshift is, and we can tell what the redshift is and how far the star is moving away from us, because the entire signature is shifted. So the number Z is the redshift. I just put this table up to illustrate. It tells you how many years the light has traveled before we saw it. And so, so a redshift of 1 means that the light was about 7.7 billion years distance. And because the star or galaxy has not stopped moving since we saw it, the current position is about 10.1 billion years. And as I said, the farther away, the faster they move. So when you get all the way down to a redshift of 10, we're talking about something that was 13.1 billion years away. So very close to the beginning of the universe, which would have been, which is 13.8 billion years. But since that object is still rapidly moving away from us, its current position, because the universe has expanded, is now 26.5 billion years from us. So I mean, these kind of numbers just boggle your mind. And again, 1 light year equals about 6 trillion miles. So getting back to the Webb has 4 main instruments in a box known as the ISIM. And that's behind the primary mirror, which I'll show you later. So it's got the near-infrared camera, the NIRCam. It's got the near-infrared spectrograph. So that's an instrument that looks at elements and takes the spectral image of that element, so they could figure out what the redshift is. They've got a mid-infrared instrument, or the MIRI, and then they've got a fine guidance sensor. So you can see the drawing of the instrument box. All those instruments are in one box, and they're behind the primary mirror, where the light finally comes out of and is observed by these instruments or measured by these instruments. Webb's main stated missions are to explore the early universe. You know, we have a couple of theories how the universe came into being, so they want to look for more further evidence of this to see if they could substantiate it. look at galaxies over time. They'd like to see the earliest galaxies they can so they can study galaxy formations. How did the earliest galaxies form? The same with star life cycles. They'd like to collect more information on the life cycle of a star. And then finally, to look for other worlds, exoplanets, which are planets outside of the solar system. So as I said, one of the major goals of the Webb scope is to explore the earliest moments of our universe. And astronomers use that redshift to measure the approximate distances of very distant galaxies. Right? They want to see how old that galaxy is, how far away it is. When you look back light years away, you're actually looking back into time. You're doing some time traveling. Because if you see something that's 1 billion light years away from us, that means you're looking at the object as it existed 1 billion years. That Eagle Nebula I showed you, that's 6,500 light years away. Studying a nearby star cluster there, scientists think that one of those stars went supernova about 6,000 years ago and probably blew that entire structure out, so it doesn't even exist anymore. But it's going to take us 500 years for the light to get to us to see if the scientists are right about their prediction. And so we're always looking further and further in time. When you see something that's redshifted 13.1 billion years, you're seeing something that's only a couple 100 million years after the Big Bang. So we're looking way back. Another thing is that, as I said, the light travels, it's redshifted. So we may see a far galaxy or object redshifted by 10 that was giving off ultraviolet light. But because of such a radical shift, that ultraviolet light shows up all the way at the other end of the spectrum as infrared light by the time it hits our instruments. So there's some real interesting factors in observations when you're looking out there. So this slide is just kind of given two theories of the formation of the universe. The top one is a standard model where after the Big Bang, the universe was hot soup for a couple thousand years. Then it started to it's a very sentimental, temperamental laser. Anyway, we have the dark ages where we had the reionization of the universe. And then you see the first stars show up, and then galaxies, and then galactic evolution. Right out to the right is standard history, or of modern days. Left is the Big Bang. Down below, some scientists have thought that there were primordial big black holes formed in the earliest time after the Big Bang, and that the first stars showed up earlier than we had thought. And so hopefully the James Webb's going to help settle that argument for us. And then there's another argument that the Big Bang happened all over at once, which gives me intellectual constipation. But we'll see what the James Webb's observations have to say in a little while. But there's all kinds of theories. And we're looking for population 3 stars. Population 3 stars have been theorized about, but we have not observed one yet. And what that is, the earliest stars formed when there were no more, when there were no heavy elements, right? There was just hydrogen and helium. Stars today that are forming also have trace amounts of heavy elements that were formed by earlier stars and then spread through the universe by supernova explosions. So population 3 stars are thought to be bigger, hotter, and have slightly different characteristics than the stars that we're seeing forming today. So that's another thing that they're looking for. I also said another major goal is to look for exoplanets, planets outside of our solar system. And scientists, one of the methods scientists use to discover them is the radial velocity method as a way of detecting these exoplanets. And it's looking at redshift. Whoa. Okay. We just had a bear show up and scare okay. So take a deep cleansing breath and you'll be good. So a planet does not cleanly revolve around the sun. What really happens is that the sun and the planet revolve around a center of mass, and usually that center is inside the star, but it's not the center of the star. And so an exoplanet that's orbiting a star will cause that star to wobble, and it'll cause it to wobble enough that we'll see a change in the redshift and sometimes a blue shift as it wobbles a little towards us. And that's one of the popular ways of finding. Give me a minute here. Oh, I don't know what happened. Hold on.
Sorry about the technical difficulties. My boyfriend decided to scare me.
Okay, here we go. Let's see, we had the radio. Oh, one other thing about radial velocity. It's the second most popular or most productive way of searching for exoplanets. We found about 935 exoplanets using that methodology already. The most productive is the transit method, where a planet will pass in front of a star, and it'll cause such a slight variation in light, but it still will cause a variation in light, and we have instruments that are sensitive enough to measure that. So we look at candidate stars and measure the light output, and when that planet goes in front, we'll see a very, very slight dimming. And we've discovered 3,900 planets using that method already. That's a very productive way. This is an image of a star, HIP 65426. Very, very cool name there. In July 2017, the European Southern Observatory discovered this super Jupiter-sized planet orbiting the star. And the designation for the planet is the same as a star, except they put a B at the end. The second planet that they discovered orbiting this star. And the system is about 385 light years away from us. But what's really exciting about this slide is the 4 images below. The James Webb actually captured a exoplanet directly for the first time ever. And those are the images you see down there. The image was seen is as seen through 4 different light filters. The near infrared camera are the 2 images on the left, and they just show how Webb's powerful infrared instruments can capture worlds beyond other solar systems. It's a real teaser pointing us to what the Webb can do. I mean, it's only been up there a couple months, and we've got all these amazing images that are rocking the astronomical world. The two images on, as I said, the 2 images on the left were on the NIRCam. The 2 on the right were the mid-infrared. So there's 2 different wavelengths: near infrared, mid-infrared. The way the images look are really a function of the cameras themselves, and those lines are not on the left are not objects. They're just artifacts from the way the telescope is made, and I'll talk about that. They're artifacts from the optics of the telescope itself. So that's been an amazing discovery. So I'm going to spend a little time comparing the Hubble and and the Webb with a couple of side-by-side images. So on the left is the Hubble telescope, and the right is the Webb. The Hubble sits in low Earth orbit. It's about 340 miles up, and it goes around the Earth, obviously. But it's too close to the Earth and Moon. It's for the heat of the Moon and the Earth would affect the James Webb telescope. So we had to put the Webb telescope way out there. Again, Hubble was primarily a visible light instrument with some ultraviolet and near infrared. The Webb is put in a place called the second Lagrange point, which is 940,000 miles from Earth. So 340 miles from Earth on the left, almost 1,000,000 miles from the Earth on the right. And the Webb uses 4 onboard instruments, which we've already talked about. Surprisingly, advances in engineering have allowed us to build a more advanced telescope that's larger, and it weighs 14,300 pounds. And compare that to the Hubble's weight of 27,000 pounds, which is almost twice the weight for a smaller telescope. That 27,000 pounds includes 2,500 pounds of upgrades that we've done to it over the years. So as I said, the Webb sits at the second Lagrange point, 940,000 miles from Earth. A Lagrange point are points of equilibrium for small mass bodies under the influence of 2 massive orbiting bodies. So the 2 massive orbiting bodies are the Sun and the Earth, and the small body is the telescope itself. So it's kind of like an eddy in a river, where something can just sit there and not be carried away by gravity. In the river, it's obviously the current. So the Webb's not orbiting around the Earth; it's orbiting around the Sun with the Earth. It's in a stable parking spot. L2 allows the Webb to keep its back to the Sun and its shields at all times, so we don't have to worry about the Sun at all. The Webb telescope always has its back to the Sun. There's a big shield that takes care of it, and it points out. And although the Webb is not subject to as much space junk as the Hubble, because there's a lot of space junk orbiting the Earth, it did already get hit by a micrometeor ride at May 22nd, 23rd. You might have heard a little piece of dust hit it. I think it was like 37,000 miles per hour, hit one of the 18 segments, but thankfully it did not cause much damage and did not affect the operation. And we've had the Hubble and the space station have been hit by those for years and years, but when you're dealing with a very sensitive mirror, it is a concern. So let's compare some of the images and see what our $10 billion bought us. On the right is the first picture from the Webb telescope. It was released in early July, and it shows an amazing increase in revolution when compared to the same deep field that the Hubble took on the left. You can see a great increase in resolution. You can also see in both of them some arcs. Let me see if I can get this. Ah, it's back. See these arcs? That's the effect of gravitational lensing. And if you've heard any of my talks from before, I always kind of mention it because I'm just amazed by it. When you have a really super massive object, like a cluster of galaxies like this, it bends space-time, just as Einstein predicted. And what happens is that you can see objects that are behind the cluster of galaxies, and they're magnified, but they're very distorted. So these are galaxies that are actually behind this cluster of galaxies that have traveled a different light path because it was bent by the massive gravitational force of that galaxy cluster. Here's a split image with a Hubble image on the left, part of a Hubble image on the left, and a Webb image on the right. This is the Southern Ring Nebula, about 2,500 light years away from us. It's easy to see the extra detail that the Webb telescope produces. As I said, its mirror is about 3 times larger than Hubble, and any astronomer knows that the bigger the light bucket, the better. And also, this scope is fine-tuned for capturing in the infrared. So it just is amazing. It's near infrared on the Hubble, and it's infrared on James Webb, near infrared. But the James Webb is just finely tuned to do these near infrared observations. Here's 2 more of the same Southern Ring Nebula side by side, both taken with the Webb telescope. The one on the left was taken with the near-infrared camera, and the one on the right is with the mid-infrared camera. So you can see how both of them produce information that's important and overlapping, but also some exclusive information. On the left, the white dwarf appears, you can hardly see it, it's really for one of these diffraction spikes. And here, the white dwarf is right here. This is another star that happens to be in the field. But the white dwarf is interesting to us because a white dwarf starts out about the size of our sun, within 8 times the size of the sun. And after it's done burning hydrogen, and starts burning helium, it starts to expand and slowly turns into a red giant. And what happens is it blows off a shell that's about half the mass of the star. And that's the ring that we see. This is about half the mass of the star that's been blown off as a star now leaves the main sequence and starts to die. It becomes a red giant. When our sun does that, we will be inside of the red giant star that the sun will produce. That's in about 4.5 billion years. And then so half the mass is in a gas envelope, and the other half is a white dwarf, which stops having nuclear fusion and takes 1 trillion or 2 years to cool down. Who knows for sure? If the Earth is only 13.8 billion years and it takes 1 trillion years for these things to cool down, we have not seen one that has gone out. We've seen the smaller dwarfs. We've seen brown dwarfs, but they didn't start out as white dwarfs. So anyway, we can get all kinds of information about the white dwarf and just the structure. You look at this structure, you could see that there's a couple of rings worth of gas, and so this particular white dwarf, as it was dying, was pulsing out gas, and that helps scientists look at the stellar evolution and the death of a star. Again, this is Hubble on the left and James Webb on the right. About 290 million light years away from us is Stephan's quintet. It's a group of 5 galaxies located in the constellation Pegasus. And again, it's very interesting. It's notable for being the first compact galaxy group ever discovered. It was discovered in 1877 by the French astronomer Edouard Stephan. It's also a favorite object of amateur astronomers to find. They love to look for it. But its real claim to fame was it appeared in that Christmas classic, It's a Wonderful Life. I think I remember seeing it. I think they might have represented angels with it or something. But they definitely had a milky white. There was no color in it. A picture of Stephan's quintet in there. Here's the Webb image by itself. And as of July, it was the largest Webb mosaic released. It it includes 1,000 images from the Webb stitched together. And it offers astrophysicists new insight on the gravitational interaction of these galaxies. The leftmost galaxy, NGC 7320, is really not gravitationally interacting with the other galaxies. It's about 40 million light years away from Earth, where the others are about 290 million light years away. And you can see there's 1, 2, 3, 4, 5. So these are interacting. You can see how they're gravitationally affecting each other. These two are very, very close. That's kind of like what the Milky Way and the Andromeda are going to be doing in about 4 billion years, interacting like that. But NASA calls this quintet a fantastic library for studying how interacting galaxies trigger star formations with each other, how the gas in these galaxies is being disturbed. Rarely do scientists get a chance to see these processes, which are fundamental to all galaxies, in so much detail. I mean, you can see here new stars being born. It's just, I'm sure it'll offer scientists years of study. Tight groups like this may have been more common in the early universe, when their superheated infalling material may have fueled some very energetic black holes called quasars. Even so, the top galaxy in this group, NG 7319, harbors an active galactic nucleus, a supermassive black hole that's estimated to be 24 million times the mass of the sun. It's actively pulling in material, and it puts out light energy equivalent to about 40 billion suns. So we know that black holes don't let light out, but there's an accretion disk around that black hole, which is how we find black holes, by their accretion disk. And the energy created and the heat created by that accretion disk as matter's being sucked into the black hole gives off this light and this energy equivalent to 40 billion suns. It's amazing. President Biden unveiled this image of galaxy cluster SMACS 0723 on July 11th. It was the Webb's first deep sky field image. And if you took a grain of sand and held it out at arm's length and looked at the sky, the amount of sky that grain of sand would cover is about the same area that this picture covers. So there's a lot of stuff out there when you think of that. This is just a grain of sand's worth of arc in the sky. Just amazing. The galaxy in the middle, SMACS 0723, the galaxy cluster, again acts as a gravitational lens, and the sure sign is when you start seeing those arcs around it. So again, there's a lot of distortion, but it's magnifying a galaxy that we would not be able to see had it not been for gravitational lensing. Some of the galaxies we are seeing here are less than 1 billion years after the Big Bang. So we're really looking back. We're looking 12 billion years and change back in time when we look at some of these gravitational lens. The galaxy cluster itself is 4.6 billion light years away. So just looking at that cluster that's doing the lensing, you're looking at something 4.6 billion years ago. The image was taken by the near-infrared cam at different wavelengths and exposures. 12.5 hours worth of exposure from the James Webb telescope to make this deep sky image. The same field was imaged in the intermediate infrared, the medium infrared, and cut through even more dust. SMACS can only be viewed from Earth in the southern sky, so there's no time of the year where we can see this this galaxy cluster. And then that's the Hubble view of it, just to give you an idea. You just don't get the same resolution. Now, going back to this, you see these, you see the stars with 6, and if you look carefully, there's another one there, like 8 different points. Those are called diffraction spikes. And to understand what a diffraction spike is, we just got to take a quick look at the telescope's design. There are refractor telescopes, which is like the one Galileo used. It's a lens after lens after lens. They're heavy and they're very expensive. A cheaper way and a lighter way to make a telescope is to use mirrors. And I think all but one telescope out here on the field are reflectors, because astronomers generally don't have a lot of money. So a reflector, you have a primary mirror. It's a parabolic mirror. That means it's curved slightly. The light comes in where it's looking, hits this primary mirror. It hits this secondary mirror, and then it goes into this tube. It's directed into this tube, and then there's an instrument box behind it. And so you can see the secondary mirror has to be supported with these arms. And that's what causes the diffraction spikes. It's part of the design of the telescope. You'll see it in the Hubble images. Even some of the brighter galaxies, you'll see the diffraction spikes as well. Just another point, just a couple things to point out. So this area is towards the sun, right? This is the shield to keep the whole telescope away from the sunlight and to keep it cool. A person standing would be about this high. That's about a person standing up. There's the antenna. Since its back is to the sun, its back is also to the earth. So there's the antenna on the back side. The instrument box is right on the other side of this, in the back of this. ISIM is the instrument box. There's the sun shield. And so that's it in a nutshell. That's why when you look at those stars, you see those diffraction spikes. It's just, you can't help it. Let's see. Okay, that was the Hubble. Oh no. Okay, so this deep field image was released on August the 2nd, so not too long ago. It includes the most distant known star, and the distant star was seen again because of gravitational lensing. So there's a galaxy group here. I'm going to show you an enlarged picture so you don't have to squint too much. But here's the arc that we're talking about. This is just a nearest star, but this is the area of interest in this deep field. A galaxy cluster causing gravitational lensing, and this arc called the sunset arc. Here it is magnified. There's that group of galaxies. Here's the arc. And this is what we think is the oldest star to date. Until this year, the oldest star observed was about 4.4 billion years after the Big Bang, which is considerably later than the first period of star formation, those 3 stars. But now, thanks to gravitational lensing, the Webb telescope has imaged a star that astronomers think is shining about 900 million years after the Big Bang. So that's 12.9 billion years ago. Much older than any single star that we've seen. It may be one of those population 3 stars that I mentioned earlier. It's found in that arc, and they named it WHL 0137. You'll never remember that, but you know, I hope some of you go on Google and just Google some of these images from the Webb. You know, we pay for it with our tax money. They're public domain images. The Webb telescope has its own page, NASA's JPL. You can find an amazing amount of information there. Everything I've shown you here, I've taken off the Webb. I have no secret contacts at NASA. I've just grabbed photos off the Webb, and you can do the same thing. And it beats watching science fiction, because this is real. I love science fiction, but this is real science, and to me, it's even more amazing than science fiction. But speaking of science fiction and fantasy, uh, because it's got such a funky name, we've also named the star Earendel, and Earendel means morning star or rising light, but it's also the half-elf character of J.R.R. Tolkien in his book Silmarillion. So it's a Tolkien character, and I know that it was definitely named with that in mind. The current estimate is that this star has a mass between 50 and 100 suns, so it's 50 to 100 times larger than the sun. It's got a 6.2 redshift, 12.8, 12.9 billion years away. And because the universe is expanding, this star is now 28 billion light years away. The star was actually discovered by Hubble, but the Webb will enable us to perform a lot of spectral analysis that will give us even more information of early stars. And we may even be able to tell if it's a population 3 star. I have no idea how they're going to do that. And then for any fellow nerds out there, this is a drawing. I don't know how they figure this out, so don't even bother asking in the questions. I don't know how they figure out the magnification line of a gravitational lens. It's just amazing. But they've drawn this line. Here's the arc. Here's Earendel. This is the magnification line. So apparently this is a mirrored star cluster on both sides of Earendel. It's the same star cluster, but it's mirrored somehow. The science behind this is way beyond me, and I'm not, and I just don't have the time to read up on it, even assuming that I would understand if I read it. But I thought that was just an amazing picture where they can actually show the line of magnification. It must have, they must, since Einstein's equations predicted gravitational lensing, my guess is that somehow they've adopted Einstein's relativity equations to figure this stuff out. So tonight we've seen, only 3 months after the Webb's gone operational, we've seen how our knowledge of star formation, galaxy formation, universe genesis, and exoplanets have all benefited from our $10 billion telescope. And I'm really looking forward to seeing what surprises the James Webb has in store for us, stuff that we haven't predicted or have no idea is coming. I'm sure there's going to be plenty of that. So that's my James Webb telescope update. Thank you.
All right. Thank you, Walt. Thank you, everyone who's here. Just before we are going to have a Q&A question. I did notice a couple of you guys here sneaking in during the presentation, so I'm going to go over the safety briefing real quick again. If you need to use the bathroom, that is to my right, your left, with the red light on it. If you want to check out our museum and gift shop, I'll be in there manning the desk after the Q&A session. We do have the Greenwood telescope, which is in the red shed towards the back of the house. And we have, I want to say, 2 or 3 scopes in the sheds directly to my left. That being said, if when you go to leave, please use your headlights because we like not getting run over. It hurts. We prefer not to. Also, flashlights, keep the lights pointed towards the ground because as much as we enjoy not getting run over by cars who have no headlights, we also enjoy preserving night vision when we can. That being said, any volunteer will gladly ask your questions. Do please follow the directions. And with that, we're going to start getting into Q&A. For the people here, I am kind of blind. So when you have a question and I call for a question, you might need to raise your hand and then wave it about a bit. Because it's dark and I've been staring at a screen. So I have no night vision. All right. I'm going to start us off with a question from our online audience. And the first one is, have we gotten news of another scope that they probably have in the works? Or is the current focus more on getting back to the moon and eventually Mars?
I would say yes. Yeah, I think it's more getting to the moon and possibly Mars. They just put this James Webb. This was a huge project, and there's a lot of people devoted to it, and we haven't even scratched the surface. They may be planning one. I mean, the James Webb took about 20 years of planning and funding to get up there. So they may have a successor in mind, and we're always putting up smaller telescopes to look at different spectrum. But yeah, I don't know. I don't know of anything the scope of the James Webb's in the plans.
All right. Any questions here? Again, anyone? I hear a lot of crickets, and not just because we're in a state park. All right. So our next online question is: you actually went, I think, over something similar at the end, where you told us the approximate age of the oldest thing the James Webb has image. Have they estimated the distance of the farthest thing the James Webb telescope has imaged?
Yeah, it was 13.2 billion years. That was a galaxy. I think it was ZD1, but that has not been confirmed.
All right.
The distance. You know, as I said, it's interesting. They're doing something a little different than when the Hubble came out. When the Hubble came out, they looked at a lot of the images, and then they released them later. And with the James Webb, they're releasing these images before they've done the spectropody or any of that stuff. And so we're seeing this stuff before they've really analyzed it. They're telling us generally what we're seeing, but they'll tell us approximately how far they think it is, but they need to verify that by really looking at the spectrometers.
And also, unlike the Hubble, a lot of science actually gets done by amateur astronomers and citizen science, where people decide to go on a weekend for fun and figure out math. I mean, I do spreadsheets for fun, so I can't even say anything, but that's besides the point.
No, there's some cool projects you can get involved in. There was one that's been around for years called Galaxy Zoo. And you can sit there and you can there's so many galaxies we have pictures of. Scientists don't have enough time to classify them all. So you get a little tutorial on how to classify galaxies, and then you can classify them and help do the science.
Right. Question from the audience? Oh, I see one. I might have. Oh, no. I know where you are.
So how long does it take for an image to get from that to us?
Well, it's only a million miles, so you know, the moon, it takes just a few seconds to get light. So yeah, it's a matter of seconds. It's a noticeable delay, but it's not that long. A million miles is nothing, as light and radio waves travel at 186,000 miles per second.
All right. Was there another audience question? All right. I do have another online question. And actually, we just answered this. They asked, is there a public database where we can just find images from the James Webb like there is for the Hubble? And I believe you just answered that, yes, there is.
I think it's jwst.org, but just Google James Webb, you'll get there.
All right. If at any point you have a question, raise your hand, wave it about, or just wait, unless you don't care, and then raise your hands anyway and wave them around like you just don't care. All right. So next one, we got someone asked, did you mean the James Webb is making a mosaic of an image, like they take a picture of one area, then shift it to the next area and the next area? Or is it like how astrophotographers might stack images where it's the same area and multiple images and they kind of stack out the noise?
Right, and they can do both. But when they say a mosaic, they're stitching images together. They're taking images of slightly different parts of the sky and they're stitching them to make a wider field image than is possible with this telescope taking just a single exposure. But there is also stacking possible, and it's amazing though. The James Webb, I showed an image that was 12.5 hours worth of exposure time. That's huge. Astronomers here, when they take pictures now, digital photography has really come a long way since the days of film, when I had to really. It hurt to do astrophotography when you use film. But now you can take 100 60-second exposures, and there's software just to stack them. You can take a picture using a webcam and get 2,000 images of a planet, and then have the software pick out the best 1,000 images and stack them all together for you and get an amazing photograph of a planet that you could never have done in the film days.
All right. So I'm going to put out a last call for any questions on our online chat, and I'm just going to give it a minute because unfortunately there is stream lag. When I say it, it takes a little bit for them to hear it. Were there any other questions here with our audience? Oh, we got one.
No, it's just a follow-up to the citizen science project. If the computers can do all that you just mentioned, why can't they classify galaxies? Why do we need humans to do that?
Because it's still just artificial intelligence, and sometimes you need real intelligence. No, I'm sure they have machine learning that they'll get there sometime. But as far as classifying the galaxies, I guess they just cannot look at dim objects yet and classify them with the accuracy that humans can. I hope they don't take all the opportunities for citizen science away from us and give it all to machines. Machines don't enjoy it. They just do it.
And what you can actually see if you're on the online audience is she's actually wearing a really neat, nifty sweater for medical for Starfleet. She said it was for a Renaissance fair. I'm kind of jealous, though. All right. Any more questions? All right. So I want to thank everyone for coming out. Like I said, we do have a number of telescopes open. If you ever can't make it here, you can always join us on the online side. We do live stream onto YouTube. If you're here, do like and subscribe to our channel. It does help us out, and it lets us know that people are out there watching. And with that, have a good night, everyone.